In this video, I'm going to talk about even and odd functions. So let's start with just defining what it means for a function to be even or odd. A function is even if f of negative x is equal to f of x. A function is odd if f of negative x is equal to negative f of x. And then a function is said to be neither even or odd if the above statements, these two things, are not true. So these are just definitions of what it means to be even and odd. Notice in both cases, we have to see what f of negative x looks like. So that's always where I'm going to start. When I'm trying to determine if a function is odd or even, I'm always going to start with the negative f of negative x. A function can't be both even and odd. So if we can show that f of negative x is equal to the original function, great, we're done. If that's not true, that's when I'll go on to see what negative f of x gives me, and I'll see if that is in fact equal to the f of negative x. So let's just jump right into an example. Let's determine if the following functions are even or odd. And we'll start with f of x equal to 3x squared plus 5. So, again, using my definition statements here, I'm going to look at what f of negative x looks like first. So I plug the negative x in for my old x, 3 times negative x squared, and we know that negative x squared is just going to give me a positive x squared, so I get a 3x squared plus 5. If we compare that to the initial, those are in fact the same. So what that tells me is that f of x is even, and we're done. We don't have to test if it's odd because we know it's not. We found it to be even. Let's take another example. Let's take g of x equal to 4x cubed plus 2x. So I'm going to start off the same way. I'm going to plug in the negative x. I've named the function something different, but it doesn't change what I'm doing. I'm plugging the negative x. So I'll have 4 times the negative x cubed plus 2 times the negative x. And when I simplify this time, well, a negative x cubed, a negative cubed is going to give me a negative. So I have 4 times negative. It's going to be a negative 4x cubed. And then a 2 times negative x is a negative x. So negative 4x cubed plus, minus x. And clearly, if we compare that to the first, they are not the same. So what that tells me is g of x is not even. That does not guarantee it's odd. Remember, there's a third option that it might be neither odd nor even. So we've got to go on and test to see if the function is odd. And to do that, I'm going to place the negative in front of the g function. Keep that g function in parentheses because I'm going to have to distribute. And so when we distribute, we get a negative 4x cubed plus, if I distribute it, that should be a minus 2x. And now that I'm going back and looking at my work, I knew what this function should be. That is not the same as what this was, but I left off a 2 there. I think I said it and I just didn't write it. When we take 2 times the negative x, it should be a negative 2x up here in this line. So now that I have that corrected, if I compare my negative g of x to my g of negative x, those are the same, which means g of x is odd. So notice here we're comparing negative g of x not to the initial. That's not what the definition tells us. It tells us we have to compare it to g of negative x. Because those two things are the same, we end up with verifying it is in fact an odd function. Now you may have noticed something in these two examples. We had purely even exponents in f of x, and then we had the 5, which is a constant. And then here we had purely odd exponents. And the even exponents gave us an even function, the odd exponents gave us an odd function. Notice the coefficients didn't matter. We had even coefficients on the odd function and odd coefficients on the even function. That didn't matter, but the exponents actually seem to kind of tell us what the function is, and that is true in the case of polynomial functions. Polynomial functions, the exponents, that's why they are even and odd functions, because those exponents are working out in the same way over and over again. Those even exponents will always keep my signs to be the same as what the original function was, while the odd exponents are always changing the sign from what it was. So then maybe the question becomes, what happens when we have a mixture of the two? So let's say we have a 5x cubed plus a 3x squared. I'll plug in the negative x. And as we would expect, the negative changes signs. The odd changes signs. It becomes a negative, so we have a negative 5x cubed. The even retains the same sign. So if we compare that to the initial, they're not the same, and so it's definitely not even. So I'll go on to test if it's odd, and to do that, I'm going to put the negative in front of the function. I distribute that negative. And so compared to the original, the odd component has changed, but now the even component has changed as well, which means it's not matching up with the h of negative x. So that's telling me it's not odd. So in this case, h of x is neither odd nor even nor odd. And so if we have these mixture of the two exponents, they're both kind of behaving as we would expect. One's behaving as the odd, one's behaving as the even, and so that gives us something that is neither. Now, these shortcuts only work in the case of polynomial functions, things raised to powers. If we have fractions, if we have square roots, cubed roots, absolute values, trig functions, logs, any other type of function, then we can't just apply these shortcuts to. We're going to actually have to go back and test using those formal rules. So we do need to be aware of how these rules work. And I'll do another example or two of some of these different functions, but do be aware of that we can't just expect these simple exponent rules to work for every single type of function as just the polynomials. I also do want to just point out too that notice back here this constant component, constants always behave as an even exponent. It doesn't matter what the number is. The constant will never change in sign, so that's always going to behave as an even. Let's take another example that's not purely polynomial. So let's say we have x times the square root of x squared plus 3. So if we simply look at the exponents, which would be incorrect to do, we notice that we have an odd exponent and an even exponent. So maybe for a second we might want to say that it's neither, and that would be completely false reasoning. Let's use our test to see what it actually is. So I'm going to start with the negative x. I'm going to plug that negative x in for both of the old x's. And so the negative x out front stays, but inside that x squared becomes a positive. And so we can see that it's definitely not the same as where we started. It is not even. Those are not the same. Next, I'm going to plug the negative in front. So I'm going to have a negative x times the square root of x squared plus 3. Notice here, this is all one term. There are not multiple terms. There's no pluses and minuses separating the x from the square root. So when we distribute the x, it just goes on the whole expression once. And once we simplify that, if we compare it to the f of negative x, we can see that they are in fact the same. So this is an odd function. F of x is odd. So again, we can't just always rely on those exponents. That only works in the case of polynomials when nothing else is going on. We need to be aware of how the tests work. Let's do one last case. I'll call this last one g of x. And we'll take x plus 3 over x minus 2. I'll plug in my negative x first. So I'd have a negative x plus 3 over negative x minus 2. Now, this is a rational function. It's a fraction. These we have to be the most careful of because, remember, we can always factor out a negative from top and bottom, and that would be the same thing. So if I were to pull out a negative from top and bottom, we'd have a negative x minus 3 over negative x plus 2. And then we can cancel off those negatives and get x minus 3 over x plus 2. And so that is not the same as what we had just a second ago. So it's not even. Now, can recognize a little bit faster whether it's going to work out to be the same or not when you pull out that negative. If all of your signs are wrong, it's actually the same expression, because by pulling out that negative from all terms, you're going to switch all the signs. But that is something to be aware of with fractions, that you have that ability to pull a negative out of top and bottom. It results in the same fraction. But notice, this thing here definitely does not look the same as that initially, but they are the same once we realize we can just factor out that negative. If I put a negative in front of the fraction, here we have the option of where to distribute that negative. We can distribute it across the top, like so. We could have also distributed across the bottom, like so. So both of these are equivalent. Again, that idea of just pulling out or factoring out a negative from everywhere would get us from one to the other. And so if we compare either of these to what we see above, notice it's not the same, because again, not every sign is backwards. The x is backwards, but 3 is the same. And so these two things are not the same. So this is not odd. This g of x is another example of something that is neither even nor odd. Now, that is the formal definition of how we determine if a function is even or odd. Those are the formal tests for how we can do it every single time. We need to know how to do that. But if we're given the graph of the function, it's actually a little bit easier. We can look at the symmetry. If a function is even, the graph will have symmetry about the y-axis. And if a function is odd, the graph will have symmetry about the origin. So I'm going to hand sketch these and we'll determine. So as an example of an even function, think about the polynomials we're just talking about. The simplest polynomial function that would be even would just be a constant function. Something like maybe y is equal to 2. Notice this is symmetric about the origin. If I were to kind of draw this dotted line here on, not the origin, excuse me, on the y-axis, if I were to draw this dotted line on the y-axis, or think about taking this as a piece of paper and folding it along this axis, this looks exactly the same as this. So this is an odd function. Excuse me, this is an even function. It has that symmetry about the y-axis. If I were to take another example of an even function, another very simple one would be the x squared function. Perfect parabola, where this is meant to be my vertex. It's not perfect. Maybe try that one more time. That looks a little bit better. And same idea, we can see that it is symmetric about the y-axis. It doesn't mean we have to pass through the y-axis. So, for instance, I could have the rational function 1 over x squared, and it doesn't actually pass through the y-axis. But if we look, it is mirrored on both sides of the y-axis, so that is another example of something that is even. Symmetry about the origin is a little bit more awkward. So an example of that would be the x cubed function. Looks like this. And what I mean by awkward is just harder to, we can't fold in the same way we could with the y-axis. We can't just fold our paper in half, but the way I encourage you to think about this one, it's like a rotational symmetry. If I were to take my pencil and I had a piece of paper and I put my pencil down on this point right here, and I rotate my paper 180 degrees. If I get back to the same picture, that is in fact an odd function. So this one is odd, has that rotational symmetry. Another example would be the rational function 1 over x. This is an example of one that doesn't actually pass through the origin, but that doesn't matter. If I were to put my pencil right here, rotate 180 degrees, we see that we have the same picture, so that is odd. If we take something that looks like this, there's no symmetry here. It's not symmetric about the y-axis. It's not symmetric about the origin. We can't rotate it. This would be an example of something that's neither odd or even. If we were to take the x squared function that's not sitting on the y-axis, this is also not, it's neither odd nor even. If we reflect about the y-axis, it comes over here. If we reflect about the origin, it goes down here. This would be neither as well. And so determining graphically if a function is odd or even, relatively simple. It's just kind of looking at it and gauging its symmetry.